All right, so projectile motion. We were working on this problem, and now we're going to sort of finish it off. We've got a projectile that launches up at an angle, comes down. Keep in mind that when it launched initially, it was at an angle above the horizontal. We already dealt with that. But it had an x velocity, and at every point along the way, it had an x velocity. Everywhere. And that x velocity doesn't change. And so though I know that, here I've made my drawings to make sure these arrows are all the same length. I know that I had a v1x here. But what I know about that v1x is that it was the same at each of those horizontal points. So that what I can say is when the object hits the ground, its v2x is going to be the same as what it started out as. I'll put it in writing, v1x, the same. You know, some people even say v average x equals v1x equals v2x. But I don't want to overdo it. It's 10.81 meters per second. We figured that out last time with the first set of parts here. And the other thing that we figured out was what the y velocity was going to be when it strikes the ground. We figured out, I think it was even in, correct me if I'm wrong, in part C, didn't we just figure out what v2y was going to be when it strikes the ground? Good, flip back and take a look. We figured out that v2y was going to be equal to, what is it? Can you guys quote it to me? 22 point something or other. Well, Phoenix, you know what the whole number set was? $493. All right. 77 meters per second. And so by the same logic that we had v2y from the last part and v1x as I just explained, we got the impact velocity, but it's not the whole impact velocity. We have to reassemble it. Remember that when this thing hits the ground, it's going to have an impact velocity that goes like this. And if I was able to, computer-wise, pluck this vector off the page and stack it tip to tail at the end of v2x, it would look like this. I would have v2x, I'll redraw it, v2x. If I had this special effect, and v2y, notice I've just taken these two vectors and I've properly added them tip to tail, because v2 as a vector equation would be equal to v2x plus v2y. And that doesn't mean 10.81 plus 22.4377. That means I've got to find the resultant of those two vectors. I try to be in my habit of writing resultants as double bold vectors. And I'd like to know the direction in which it's pointing, because v2, of course, is a vector, so it has direction. So I'll just label it up, but then this becomes my diagram for the math that we're about to do. So I've got my 10.81 meters per second. I've got my 22.4377 meters per second. You know, when I'm solving these problems, sometimes, especially as a beginner, I would do this first so I can think it out, and then I would do this. Maybe you've done a ton of your homework, you become a pro at this, you jump straight to the vector diagram. Depends on where you're at, okay? So everybody's going to be at different stages of development on this one. But when I say I want to find v2, this is just Pythagorean theorem, so I'm saying v2x squared plus v2y squared, all rooted. And if I can find that, I'm going to know what velocity this object is going to be going at when it smacks into the earth. How fast? So 10.81 meters per second. Got to square the whole thing plus 22.4377 meters per second. Square the whole thing. Square root the entire side. And then somebody with a calculator, help me out. It'll be like 29 or 24 and a bit, I think, or somewhere around 25. But I feel like I don't trust myself from last week. Somebody help me out with the calculator. Who's quick on the draw? You got it? 24.90323. 9023. Way to Way to leech off of somebody else's quick draw. I like it. All right, meters per second. So then we're going to round that off to, oh gosh, it looks like we only have 3 significant figures, right? 24.9 meters per second. Block this off for layout. We'd say, I'd like to use the tan ratio because I know the opposite and I know the adjacent. So the opposite is V2y, the adjacent is V2x. Theta equals tan inverse of V2y over V2x. Sub in my values. And again, somebody with a calculator, help me out. Give me 4 decimal places on this thing. Who's quick on the draw? Nobody wants to lose. Everyone's afraid.
I do. I'll use this thing.
Yeah. 762, you said? Okay. Degrees. And of course, at 3 sig figs, that's going to take us to 24.3, or sorry, 64.3. Beautiful. And then we're going to figure out how we're going to express this thing. So we can say, all right, well, the question was, find the impact velocity of the ball when it hits the ground at the base of the cliff. Okay, so we've done all the legwork on it. Now we just got to put it into words. So therefore, in context, the ball impacts the ground with a velocity of, we've got our magnitude, 24.9 units, meters per second, direction. Now this is the thing we want to make sure that we got right, because we said that for projectiles we will always do relative to the horizontal for our direction. So it'll either be an angle below the horizontal or an angle above the horizontal. So I just want to like scan up here. Is that an angle above the horizontal or below the horizontal? Below. This is below the horizontal, right? So we could say it's 64.3 degrees below horizontal. No short forms on this one. So 64.3 degrees below horizontal.
Rising down.
And we don't have to worry ever about it being like an acute angle or something like that. Like we don't use the smaller of 2 angles or something like we might with cardinal directions. We just use the angle relative to the horizontal every single time. And it doesn't surprise us that it's at a pretty steep angle, because that's what balls do when you throw them off the cliffs. They go off on these parabolic paths, and if I were to draw a tangent to that curve, it would make sense that it would be a pretty steep angle, right? All right, so let's talk about the 4 main types of projectile problems, because we kind of have, you know, in English class we talk about archetypes, which are like the major kinds of characters. These are the 4 major players when it comes to projectile problems, the archetype problems. One that's straight, number 1 is straight up. So in a straight up problem, that means you launch something vertically. Well, maybe it's a microphone, tossing it straight up in the air as you do the mic drop. And in that case, we might have a V1, but when it gets up to the top of its, yeah, I know, the drop is a drop. This is a throw, you're right. So I guess it's like, there could be like a level 0 where you just drop the mic, which would just be the first half, right? But for the throw it straight up in the air, you'd have a V at the top that's equal to what? 0. No one will ever forget the kangaroo. 0 meters per second, okay? And then when I come down again, we said once before that if you really do come back down to the same height from which you're launched, we can make symmetry arguments. We can say that V2 is equal to negative of V1. Okay, so that's only when you get back to the same height, you launch straight up. We got our up-down scenario. And this is the only one of the archetypes that's one-dimensional. Then we have the, really I guess I should call this 1, 2, 3, 4 with a dot, just to make sure that we know that these guys are just numbered indices. But we have the horizontal elevation. And when I say horizontal elevation, I mean it's launched horizontally from an elevation. So launching horizontally off of a cliff, and we've dealt with that stunt drivers and so on. So we'll have a V1, and this V1 is 100% in the x velocity. So I could say V1 equals V1x. But I could also say that V1y is equal to 0 meters per second. And we say that this follows a parabolic path, a downward facing parabolic path, so that when it lands on the ground, I could have a V2x. And that's just going to be equal to V1x. We actually just saw that in the previous portion that we were looking at. V2x equals V1x. But we could also say that we have a V2y. Keep in mind that this V2y would be the same value as something that just gets vertically dropped. And we talked about that in notes. And we could say, for example, on Earth, or in this classroom, AY is equal to 9.81 meters per second squared. And we have to think about that because we've got y motion here. But we also have to think about it over here. AY is equal to 9.81 meters per second squared. And we have to make sure that we define a reference frame. Now for the first one, I'm just going to backtrack a little bit so that I can go backwards so I can go forward. For this one, our reference frame would be just straight up, down. And you can choose whether you want to have up be positive or down be positive. Doesn't really matter. The point is you want to choose a reference frame to minimize the number of negative signs in your calculations, just because strategically that helps us to make less mistakes. That's all. But you have to be consistent about it. When it comes to the horizontal launch, again, we would have a reference frame for ourselves. I would suggest that if we have an up and a down, we have a right and a left. I'd suggest for horizontal launches we call down positive and right positive, just because all of the motion is either down or to the right. I just make a little note to myself. Remember, x, y, independence. And if you're following along in the notes, that means something to you, because that means that we can only have x variables go into equations together, and we can only have y variables go into equations together. The only exception to that is that time can go into both, because the amount of time you're in the air for before you hit the ground is also the amount of time you're in the air for to travel forward, right? So that's a shared variable. But everything else, the x stuff has to play together and the y stuff has to play together. Now the next archetype is angled from an elevation. And that's the problem type that we just finished, where it goes up and it comes down. And we might have a similar reference frame to the previous one, only most often I see people making up be positive and keeping right positive, but they let down be negative. To the left be negative. So that's a style choice for you. But you know, the information about this V1x being the same as this Vx, being the same as this Vx, being the same as this Vx. We just did that. It's still going to be true. And when it hits the ground, we recognize that this V2y is going to be something that's going to come out of an analysis where I would have a V1y here. I would have a Vy that's equal to negative of V1y at this point. And that reminds me of something we said earlier with this one-dimensional scenario. It's just that now we're thinking about that xy independence. And then when it hits the ground, notice that the Vy has sped up because of that acceleration due to gravity, because we still have ag equals 9.81 meters per second squared, and that's a y piece of information. It only operates in the y, so it's going to speed up that Vy as it strikes the ground. And then I'll just draw attention to this. Ax is always equal to 0 meters per second squared, which is true over here, but I'm just leaving myself space to write it here. And acceleration y is always going to be that 9.81 meters per second squared down. And make sure that we don't mix those guys up. X's can only play with x's and y's can only play with y's. The last one, I almost think that this was the hardest archetype. The last one is something that you're going to see in the homework, but we didn't really even do this archetype in example problems because you should be able to draw the information from this one for this one. Remember, we're going to have a V1x here, but for this one, we're going to travel up and come back down just to the same height. People say, well, what kind of scenario could that be? Soccer ball on a soccer field, baseball on a baseball field, golf ball on a level golf fairway. All these are good examples, right? Football, going up and getting caught at the same height, level ground. Okay, so this one is a really popular one when it comes to sports analogies or sports scenarios. But this Vx and this Vx are all going to be the same as V1x. I'll call this guy V2x equals V1x. The point is that because acceleration in the x direction is 0, it's just going to coast at a constant velocity in the horizontal direction. But then in the y direction, I look at this one and it makes me think of the very first one. What's the value of the Vy at the vertex, of the maximum height? Yeah, I got a few people giving me the 0 sign. Okay, so up at the top here, I'd say Vy is equal to 0 meters per second. And then, I know I talked about the V1x at launch. Remember, there's also going to be a V1y. And again, we already kind of covered this here and again here. V1y when it lands. And then V2y will be the opposite of that initial velocity in the y direction. So there's a lot of recurring patterns. You know what? No one of these four is exactly the same as the other, but we've got overlapping ideas that are going on here. One thing that I want to make sure that we remember, because I think that it's kind of baked into us to say, hey, if I know an initial launched angle, theta, one of our default things that we should be doing is breaking it down into V1x and V1y. But what we saw at the tail end of the last problem is that whatever the final velocity is, whether it's this scenario, or this scenario, or this scenario, the V2 is often downwards at an angle, so we talked about it as having a final velocity that's below the horizontal. And we've got to take that V2x and that V2y and use those components to rebuild the final hypotenuse, right? So whether it's through Pythagorean theorem or through SOHCAHTOA, we're going to use trig ratios and Pythagorean theorem to take that final x component, that final y component, to figure out what the V2 value is, and then use trig ratios to figure out the impact velocity. I think that's pretty much it. Those are the only four types of questions that I really think I can ask for projectile problems. So people always say, like, what should I study? You should do your homework. And you should be able to make sure that you really can do those four archetypes for projectile problems. That's all there is to it. But I'm happy to help projectiles.